All right, these are questions requested from 12-6. I'm going to go really fast. It's a video. You guys can pause and rewind and re-watch anything that you'd missed here. We're supposed to take this binomial, ooh, that's different, and raise it to the fifth power. Well, again, according to our lovely binomial theorem, it's supposed to be 1 times the value of a, which is our lovely 1 over x, to the fifth. Because this is the difference of the two terms in the binomial, we will then alternate signs. The coefficient of our next term should be 5. I have to take 1 over x, knock that down a degree to the fourth, and then the second term, the square root of x, should be to the first. No, you don't have to write that out, but I'm hoping that you'll start to see the pattern. Alternate signs according to Pascal's triangle. The next term should have a coefficient of 10, and we'll have 1 over x to the third times square root of x squared. That's not going to be too tough. I'm running out of space, so next term, again, alternate 10, 1 over x now squared, square root of x up to the third, plus, back down to 5 is the coefficient, 1 over x to the first, square root of x to the fourth. One last time, alternate signs here, square root of x to the fifth. So again, Pascal's triangle, 1, 5, 10, 10, 5, 1. Yay, symmetry. I'm sorry, I forgot the 1 here. Alternating signs, positive, negative, positive, negative, positive, negative. Okay, it's to the fifth power, so we end up with 6 terms. The first term, a, the 1 over x, goes from the fifth, fourth, third, second, first, and then disappears, implying to the 0. And square root of x, our value there for b, is missing from our initial term and then increases to the first, second, third, fourth, fifth. All right, so now it's cleanup. You guys do remember fractional exponents, don't you? All right, here we've got a coefficient of 1, no big deal. 1 over x to the fifth. 1 to the fifth is still 1. So that's simply 1 over x to the fifth. Minus, we could put 5 over x to the fourth times, now x to the first means if we're going to try and combine that with this x to the fourth component here, we should write that also as an exponent. So anything taking the square root will be x to the 1/2 power. Now, before I get to the next term, let's refresh your memory on how to simplify those. It's basically our what we called our quotient rule. So we have x to the 1/2 divided by x to the fourth. You're supposed to take the difference between those exponents. So 1/2 minus 4 will give us negative 3/2, otherwise known as negative 7/2. But again, hopefully you remember something about we're going to write it using only positive exponents. So we'll put that negative 7/2 in the denominator and say that's as simplified as it's going to get. Okay, so now on to our third term here, 10 times 1 over x cubed. Well, that'll be 10 over x to the third. But now x squared times x is, I'm sorry, x, the square root of x squared is x. So we can reduce that down, so that becomes 10 over x squared. Minus, then we'll take 10 over x squared times square root of x to the third. Remember, square root of x is the same as x to the 1/2 to the third. I mean x to the 3/2 power. use our quotient rule again. 3 halves minus 2 is the same thing as 3 halves minus 4 halves. That should be negative 1 half. So this will be 10 over x to the 1/2 power plus, well, 5 over, well, that's just 5 over x. And the square root of x raised to the 4th will be x squared. Oh, again, that'll reduce down. That gives us a nice, wholesome 5x. Minus, well, really the only thing that we can do there is square root of x is x to the 1/2 times 5. That's minus x to the 5 halves power. It's not pretty, but it is correct. For number 29, let's go there. They're just looking for the first 3 terms of this expansion. So hopefully, again, the first term, make sure you're choosing the right combinations. 20, choose 0 of x to the 20th, 2y to the 0. 20, choose 1 of x to the 19th, 2y to the 1st. And 20, choose 2, x to the 18th, 2y squared. Well, 20, choose 0, that's a coefficient of 1. And of course, this becomes a 1, so the first term is simply x to the 20th. The next term, the number of combinations of 20, choose 1 is 20. X to the 19th times 2y. So that should give us 40 x to the 19th y. And again, if you've forgotten how to do that with the calculator, menu, we're looking for the probability. Make sure you find the right combination of 20, comma, choose 2. So it'll be 190 times x to the 18th times, again, 2y squared. That should give us 4y to the 2nd. Now take 190 times 4. That should be 760 x to the 18th y squared. 33, next, find the middle term of the expansion of this raised to the 18th power. Now, let's talk about the fact that, again, if it's raised to the 18th power, that means that there are going to be 19 terms. That's how they can say find the middle one, because it's an odd number of terms. So if you, I don't know, need to take your shoes and socks off here, count to 19, the middle term will have to be the 10th term. Really? That's okay, it was my wife. All right, so again, we've got 19 terms. So if you count, if we put 9 terms on this side and 9 terms on this side, that's 18 terms. The 19th, the middle term, is going to be the 10th term. All right, so if we're just going straight to that 10th term, this is, again, The power is 18. Choose 10 to get our lovely coefficient there. And then it should be the x squared that we're taking to the I'm sorry, the way they wrote out the general term here for any particular term, that bottom number there should be n minus r. Okay, so again, in this case, n is 18. We're looking for the 10th term in this. Again, for both of these, if this is in fact the middle term, both of the exponents are going to be the same. So again, for that 10th term, if we think of it in those terms, this x squared should be to the ninth, and the 1 should also be to the ninth. Again, the sum of those exponents in every single term has to be 18. So for the middle term, yeah, both of those have to be 9. I apologize. That's got to be a 9. All right, so then the right combination out of 18, choose 9, is a whopping 48,620. X squared to the ninth will give us x to the 18th power, and then 1 to the ninth. Do I even have to write that down? So it was interesting that the first term there is x squared, but it was really simple that the second term there was just a simple 1. Find the term containing b to the 8th in the expansion of this lovely. Now, realize which term is it? Okay, now again, we're raising this to the 12th, so we know it's going to be the combinations of 12 choose. I don't know which term we're using here, but I do know it's going to be a to the r power, and I know it's going to be the b squared to the 12 minus r power. Again, the sum of those always has to, in this case, equal 12. So now if we just for a moment concentrate on this portion of it here. Again, our rules for exponents means this is b to the 2 times 12 minus r power, which means it's b to the 24 minus 2r power. And by virtue of the fact that they told us this has to be, in the end, b to the 8th, we could write a nice little equation here and say that 24 minus 2r should be the exponent 8. So if we subtract 8 from both sides, if we add 2r to both sides, we'll find out that r is actually the 8th term. So from here, we can be more specific that this is the combinations of 12 choose 8 times a to the 8th. And we already know that's going to be b to the 8th. So the tricky part here was figuring out which term contains b to the 8th in its final expansion. So now it's just a matter of, yay, calculators. Combination there of 12 choose 8 is 495. A to the 8th, b to the 8th. Hey, what do you know? Those exponents are equal. Well, they're equal to one another. That's an interesting coincidence. 43, we're supposed to now go backwards. Rather than being given just the simple binomial and asked to expand it, now we're going to use the binomial theorem and shrink it back down. So again, we know here in the end, our answer is going to be a binomial. Now, a couple of important details, very, very simple details right off the bat here. The sign of every single term is positive, so that's going to use addition. First term is x to the fourth, last term is y to the fourth, so this must be the fourth power. The only thing left now is to check this against Pascal's triangle. Is the fourth row 1, 4, 6, 4, 1? Did you look it up, or did you just presume that everything was fine? Yeah, I knew we had it somewhere. 1, 4, 6, 4, 1. And that's exactly what we have here. So this will be 1x plus 1y. That's not magic. You've got to check things with the formula. Okay? Now again, look at how it goes from x to the fourth, third, second, first, and disappears. The y's increase by a degree of 1 each time. It matches up with that particular row from Pascal's triangle. That's it. All right, so let's try this with something a little bit more interesting. Oh, look, our leading coefficient is not a 1, it's an 8. So we have 3, a to the third. We have, sorry, I'm going to start scribbling here. 2 and 1, that's a sum of 3. 1 and 2, that's a sum of 3. To the third here, to the third here. We're looking at something raised to the third power. All the terms are positive. It uses addition. If we focus for just a moment here on our value for b, read it backwards. From third, second, first, 0, that means our second term is just a single 1b to the first. But if, again, we're looking for the third row of Pascal's triangle, it should be 1, 3, 3, 1. And here we have 8, 12, 6, 1. So it should be 1, 3, 3, 1. But this is 1 times 8. This is 3 times 4. This is 3 times 2. So this first term here is not just an a to the first, but this is really 2 to the third times 1. This is 2 squared. This is 2 to the first. Our leading coefficient there should be a 2. Because again, if we use Pascal's triangle and then our binomial theorem, this should be 2a to the third plus 3 times 2a squared times b to the first, 3 times 2a to the first times b squared plus 1b cubed. So the only way to get those coefficients to match up with the 1, 3, 3, 1, knowing it's to the third power, is if we give our first term not only the variable a, but also the coefficient of 2. And then I wanted to do 47 because do you feel sometimes like they give you these really strange looking problems because they're in fact setting you up for something that's going to come later? No, really? Never? Have you guys been paying attention? numbers, they do this frequently. And again, that's the reason I wanted to do 47 with you, is because they're setting you up for something that's coming next chapter. All right, so the simple binomial here, x plus h, strange, h, where they come up with that, to the third power. With our binomial theorem, hopefully the color thing will start working here. We know that that's going to be x to the third plus 3x squared h to the first plus 3x h to the second plus h to the third. Okay, so for the cubed row in Pascal's triangle, 1, 3, 3, 1, x's decrease with their exponents, the h's increase with their exponents. Isn't that nice? Oh wait, hold on, 5 terms in the numerator. But would you look at that? The first term and the last term combined to give us a sum of 0. So this is 3x squared h plus 3x h squared plus h cubed. Oh, would you look at that? The remaining terms in the numerator all have h as a factor. So once we divide it out, that becomes h times the quantity 3x squared plus 3xh plus h squared, all divided by h. And we can, I'm going to say it, cancel. And this becomes 3x squared plus 3xh plus h squared. That's all they wanted you to do there. Use our binomial theorem so we don't labor going through and foiling and distributing and looking for like terms. We should be able to get to that x plus h, the quantity cubed, without too much fuss. And then interesting things happen from there. I wonder what's coming.